Hello. Alright, welcome back to ABI-DOS. Last episode we might have come up with a plan for altitude plotter, and I guess this episode we're going to execute it. So yeah, basically what the entire plan was, if I remember right, was for each number, there are for each number, what I believe you had to do was compare each of the numbers in the 8 directions around it. For every time there is a separate, for every time there's a difference in the tens digit, therefore you divide by 10 and check for their values. If there's a difference, then there must be a color corresponding to the higher value. So the 33 and the 28 here must have a green because green corresponds to the 30 range. And you must do that for every single number here. If you counted, if you hit a pixel, it basically means that you fill in a pixel. And I realized you could optimize this by only doing this in 4 out of the 8 directions. And the reason why is because event... Is it 4? Is it 4? Or is it 3? Is it 3? Is it 3? What if we're only 3? What if we're only the top, the right, and the diagonal, and a single diagonal? Am I missing anything? See, the comparison between two numbers on top of each other, right, settles every single bit that is between two numbers in the same column. Every horizontal settles every bit. A single horizontal will settle every bit between two values in the same column. For diagonals, is only one diagonal necessary. So for example, look at the second row, right? Let's say we only took the top left. Then this 26 will measure this, the 23 will measure this, 21 will measure this, 17 will measure this, and 17 will measure this. And if we kept going down, every single one of these intermediate... Yeah, every single one of these things that are not in a row or column with any other number will be checked on every row, even the bottom row. Wait, so could this be optimized even more? To simply be only 3 directions? And could it be any of the 3 directions? Or could I choose any of the 3 directions? Because if it was, then all I would need to do is 2 west, which is the easiest one, 2 northwest, and then 2 north. For simplicity's sake. For simplicity's sake, we only do 3 checks. We only check to our north, to our west, and our northwest. I can't believe it. That actually settles every single possible empty slot. Doesn't it? I think it does. This 22 will be the most useless because you're checking nothing. But because on every side there is going to be extra pixels in a way, you can use that as a failsafe. If you see a 17 somewhere, because you're going to divide by 10, if you see a 17 somewhere, you'll know that the pixel here has to be white. So if you only check 3 directions, that's actually going to be a lot more useful. It's going to be even better. We've basically cut our work down by a quarter doing that. Okay. So let's start creating the design for how we're going to test this. What I wanted to do is I want to move it to the position where it checks. I want it to send out the value. So let's say a number comes out of this, right? Okay, let's just say that instead of a 0, out comes a 26. So let's say we're now working with this bit over here. We're gonna move... We're going to be moving... Let's move west first. So, okay, so 26 comes out. We are going to divide that by 10. And that will give us the ones digit, which is a 2. We are going to... I think what I want to do is I want to move the... I want to move the pointer. Oh, because you read 26, you're actually going to be here, right? So you first start by moving the pointer back by 1. Then divide by 10. So it will be at this position, reading a 2. I want to next move it back to this position, then read and compare, which will call out 0 and then compare. So what about this? Can I copy this? I cannot copy multiple copies of you. Or I can for some reason, I think copy multiple copies of the exit. Okay. Okay, what I can do, I think maybe I'll try the other way where I read all of these individually. So I do this, I read, I move back by 1, then I move up twice to the 22, I read, it'll shift forward by 1, now I'll shift forward by 1 again, and I'll read again. So, okay, just to show that this will create all the necessary values, let's first set 42. Okay, let's first set the pointer position to 42. What? Oh, right. Oops. Yeah, sorry. Set the this is signal 0. I need to be at position 42. Okay. So let's do this first. Yeah. And then I'll call out a 0 here. Okay, let's see. I need to demonstrate just to make sure I know exactly what's going on. Oops. Okay, so jeez, okay. So it looks something like this. Right. So we set the position 42. It'll read out 26. It'll move back. It needs to move back by 1 first before calling, because 26 is already read. It'll move back by 2. It will call out the 26 here, move back, and then move up by 2. Call out this digit, and then do the same here. So yes, you'll get the 3 values that you need. That's very cool. And the number of bits required to pull that off is actually not very small either. There is, however, going to be another problem. which is after this. Can I do something like this? So how about this? Can I use writers? So, okay, I will write down to a checker at this point, all one below it. I'll write it down to any sort of checker. I want to see if this setup somehow gets all three different values to be written down here. Because I think it does. Ooh, no, let's connect all the wires properly first. Right? Yeah, look at that. It actually writes all values here. And of course, I can make this even better because I can divide everything by 10 first. We're only looking for the 10th digit. Meaning that, voila, you now have every value that you need to compare against, a 1, a 2, and a 2, which correspond to 19, 22, and 26. Of course, these are like kind of in reverse order. So it's kind of like I want to do a little better here, I think. But I feel like this is very good already. I do like this a lot. And this actually works because I only need 3 values instead of the usual 8 that I thought we required. But yes, this actually works. And then once I'm done, I can just release everything else. And then... well, I say release everything. I'm not sure what that really means. Well, yeah, when the next digit comes in and 3 more digits come in, it's going to release the initial 3 and rewrite. So after this, if I then repeat with the next value, which is probably going to be this 23, it's going to basically replace all 3 of these and refill with a quiet number. So that is already solved for us. That section is already solved for us. We don't need to solve it anymore. Now comes the what do we do with the data we've collected? Because we've now set the machine to collect the data we need. Right, all the data are all the numbers that come out in this row. We have put the data into the comparator. So now we have our answers. We can definitively say... or can we definitively say? Because we still need to figure out which one is larger, right? Do we not need to figure out which one is larger? We do. So I can't just use... oh, the point is I can't. The point is I can have 2 results. There's no way you're gonna get 3 results, right? But the problem is, how do I make sure there's only 2 results? Like here, if a 19 checks with... if a 19 checks with a 26, or 1 checks with a 2, the 2 is larger, right? But how is it going to know that? Like what icon would work? If I check for greater than, I'm only checking if this bit, the middle bit, is greater than the 19. If I went and checked, like, let's say I saw this 28 here, I checked it again. Okay. So, I kind of looked at it a little bit. I realized that Ranger does something very similar to what we want to do. Basically, it takes 2 values and selects a larger value. So it sorts the larger value from the smaller value, right? Yeah, it sorts the smaller value here and the larger value here. And then the top does the same. And then here it again sorts a larger value, and here it sorts a smaller value. and then they get compared. That's how the ranger works. So I might want to do something similar. The issue is that here there are still 3 possible results. One is larger, one is smaller, or they're the same. And it being the same actually now becomes relevant. If they are the same, then bad things happen. Like if they're the same, then there should be nothing between them. If they're the same, there should be nothing between them. But how do I program that? It's just, I need to extract the larger value if there is a difference, and nothing if they're the same. The difference will always be only by 1, right? Yeah, it will always only be by 1. Because there is no color for a jump of 2. Yeah, I don't think there is. I don't think there would be. A jump of 2 would be very confusing, but... I mean, I guess it wouldn't entirely be improbable if they just chose a higher value. Like here it doesn't really specify. Yeah, it doesn't really specify. Man, okay, so I'm trying to come up with a solution here. What is the goal for this comparator again? The comparator will go check if the same. If same, send a 0. I think that I can send a 0 at this point because every single tile here is only visited once, so there'll never be any overwriting. So you always only ever write the top corner, and those top corner is never within the range of another number, right? These 3 are only hit by the 29 here. It's not hit by anything else. So writing a 0 to push forward by 1 actually will work, I think, in this case. So if they're the same, send a 0. If different, send a larger value. Okay, but send a larger value is such a hard ask for me. How do I extract this larger value? So first I need to check for the same, right? Equal to sensor, we'll check for the same. There's just so many things I need to do per item here. What I could do is I could duplicate the output. Duplicating the output does actually seem to be quite useful, because I can then work on all 3 at the same time. And because there's a slight delay when I'm duplicating, I can do the shifting of bits between the output sending, which is fine by me. But I will now need a way to check for the larger value, which I can do with the Ranger tech. So this block of 9, this is 9 by 9, this 3 by 3 here, not 9 by 9. Do not ever call it 9 by 9. 9 by 9s are massive. But this 3 by 3 here, or actually in fact, this 2 by 3 here actually does most of the job for us, doesn't it? That is your... Yeah, this will already... So a 0 and 3 here, the larger one will be in the middle, the smaller one will be on the outside. So, I don't know when that will ever change. Yeah, so here the larger one will now be in the middle. The smaller one will always be on the outside. The smaller one being on the outside is fine. I think I just throw it away because we want a larger one, right? Okay. So if that's the case, if we only need this 2 by 3, then I'm very happy to use it. I'm very happy to use it as long as I can do it well. The issue is that this has to happen only after the 0 checker or the equal checker is done. Is this required? Oh yeah, this is It's just a check here. Okay, so let's just leave this in the corner. We don't actually need it for now. Can shift this entire thing up by 1. Okay. Right. So how will this work? How will this work? Okay. So this all still works fine, right? Yeah, pretty sure it still works fine. Still works fine. Okay. So equal checker and equal checker. And equal checker. You know what I can do? Probably like make this even easier on myself by just flattening this out entirely. Let's flatten this thing out entirely. Okay. Okay, so this flattens the entire thing, right? Yeah, it does flatten the entire thing. Okay. So this is about as small as whatever this machine is going to do for us. I want a 0 checker, an equal to checker, equal to checker. Wait, but the problem is that, don't we need multiple? Yeah, I think I want something a little better here than just this. I think instead of doing that, I'm gonna go for three things here. So let's do this. This, and this. Each of them will be pushed out onto a B sensor that activates it. Yeah, and the last one also doesn't need to be there, but we'll just put it in for good measure. So yeah, it will look like this. So you get the 3 different values separated properly, which are these values. And those 3 values will be used as actual bits rather than just having their numbers written down. Right? I don't know. That's what I want. I think that's what I want. The issue I'm having is just the arrangement of everything. Like everything seems to be arranged very weirdly right now. Like there's not a lot of space. There just isn't a lot of space. There just isn't. Okay. That is unless the duplication happens along this line, downwards. That could be useful. Like, okay, let's redesign this then. Okay, so what do I want to do here? I want to check if they're equal first, right? I want to check if they're equal first, right? So I want to check they're equal. And I'll hold them. So the duplicants... Well, the duplicants can't go down until... Okay, so let's pull this entire column down by 1. Let's maybe do this. I'm not sure if this works, but we'll try it. Okay. So this will be our initial check for whether they're equal or not. What? Oh, right. These are not connected. Oops. There you go. So these will all go in their positions first. Too late. Okay. Well, let's just hold it for like maybe 10 cycles. 10 is way too much, but I'm just leaving it just so. So everything goes in. It will hold. The checks will occur. If they're the same, nothing happens, right? If they're the same, it becomes a 0. Yeah. Whereas if they're not the same, I guess we'll do a not equal to then. Because if they're not the same, then this should be they should all be released, shouldn't they? They can't all be released by these guys. Like what happens here is that this can happen. Okay. I thought I'm doing a bit too much here. Alright, am I not doing a bit too much here? A not equal... So this will be released if they're not equal to each other. Which makes sense, I think. I think it makes sense. Yeah. Right. And then these will stay. Why is this a 4? When did that become a... Oh, the duplication is here. Oh, why there was no need for duplication there. So yeah. So that happens. That happens. That's cool. So if they're the same... I need to input a 0, right? Yes. If they're not the same... If they are not the same, then a comparator has to occur. The comparator is again the 2x3 machine that I did, right? Yeah. Okay. This feels a bit like this feels a bit too much. This feels way too much. Because we're not done yet. I don't think. I don't think we're done yet. Like even after all the comparating has been done, we're not actually done. Are we? Doesn't look like we're done. We have so many more components to build. We have the one that we need. Okay, not only do we need the comparator, we need the color. We need this value to link to its color. I'm definitely not doing this right. Or doing this too inefficiently. There must be a better way of doing this. The difference is always going to be 1, so we can't use a difference. The larger value is going to be... I feel like I spent way too much space here checking for equality. Way too much. There are in fact 3 outcomes that I need to build. 3 outcomes. 2 of the outcomes lead to the same result. But it's 3 outcomes either way. How can I get a 1 and a 2 to just give you a 2? Is it ever possible? Or do I need to actually like compare them and choose a larger one? Is there an easy way to choose a larger one? I feel like we would have to actually use the machine that we built in Ranger. The problem is that doesn't eliminate equalities, which I don't like. I don't like the fact it doesn't eliminate equalities. I need to first eliminate equalities. How do I do that? Well, I mean, yeah, this is the machine I'm building to eliminate equalities. They're just too big. They're just way too big. If that happened in the top row, say, where if that would happen in the top row, it's way too tough. Although, interestingly enough, I feel like it could do better. Could do way better, couldn't I? Yeah, I could do way better. Like, okay, let's go all the way back to the part where I folded everything, where I separated them. Go back to when I'm folding everything. Why don't I take this entire thing and leave it out? We'll do the writing here. Here, here, and here. And then we'll very slowly put everything back in to match that. Alright, let's leave these there here first. We'll leave these here. Get rid of the wiring. And then you will come out through the side. And there's your comparator. I mean, that works. Right? And then, you know, you guys can link to this, this, and this. Which will, I guess, a not equal will push you forward. Equal will push you. Equal needs to push you away. So let's just say for now, if they are equal, they'll just get removed. Equal doesn't mean anything except for giving you a 0. So the 19 will come out here, I think. And therefore, this one will be the only one that produces an actual value of 1. Right, this will write 2 down here, here, and here. Everything else is still working as per expected. Yeah, because all the writing happens a lot earlier than the calling of the signal, so everything will check correctly. Same here and here. This one is the one that comes out. Cool, okay. That is much cleaner for an equality check. It is so much more effective. So much smaller too. Good. Next. The equality check doesn't just have to activate these guys. Also, wait, yeah, no, not done. Yes, the equality check doesn't just have to activate these guys. The equality check can also do other stuff. The equality check can basically redirect this signal to be set to 0. Right? If they are equal, then a conveyor belt activates this and then pushes it to become 0, and then let 0 just enter the output. We have a lot of outputs, so honestly it's fine. Right? Yeah, that's good. That's good. Okay, we do have quite a lot of space for this. The problem now is that, okay, good, we have this, we still need the color coding. So let's say we build the larger one here. Let's say we build the actual holder here. Right. Let's say we do that. We want this to write over here onto a greater than. Okay. Okay, hold on. Oh, here. Okay, this is taking up a lot more space, but we'll consider it fine for now. Let's just do this first. Okay. So the idea is, if this is larger, this will activate and this will activate. And if this is larger, okay, so yeah, this should be fine, right? Oh, okay. Oh, well, I guess we just timed that very well. Yeah, this would make this 2 enter here, because this 2 is larger. This is so many spaces though. So unworth it. But this looks decent. The colors. How do I even make the colors? They're all the same number, just differently colored. Okay. Okay, so let's just say we have this. Let's just say we have this for now. I want to build the color machine and see how someone can make that. Then I know what I would like to do. So, to a new save slot. What I want to do with the colors, actually. So we'll do that before leaving. I think that's what we're gonna do, and I'll think about the thing even more. But we use Y because Ys don't produce a bit at the very beginning. So we can perhaps trigger each of these Ys based on a certain value, right? So the value is 1, we're in the range of 1 to 19. If it's a 2, we're in the range of 2 to... yeah, and so on and so forth. So this is generally what our machine will look like. Then, okay, so we need a total of 4 colors. Our 4 colors will look like this. I'm almost certain there's a very easy way to make this happen well. Okay, so let's look at the colors. One is purely red. 2 is yellow, which is a combination of red and green. 3 is green. And 4 is cyan, which is a combination of green and blue. That's really interesting. Maybe we do a color mapping instead, where there are only 3 Ys. Okay, so okay, let's just put this color code, this color map all the way on the side first. Instead, I want 3 Ys. Each Y produces a specific color. So one produces red, one produces green, and one produces blue. Each of these values will activate the necessary items. So 1, for example, will activate only red. A 2 will activate red and yellow. A 3 will activate only green, not red and yellow. And then a 4, well, the 4 has to activate, the 4 has to activate green as well. That's kind of the issue, right? Green is activated by 3 different values. which means you can't use... You don't have a third wire color, which is very sad. Why don't I have a third wire color? I need a third wire color. Well, another thing I could probably do is just connect this to another Y port here. And there you go. That makes it... I think that works. So if a 3 comes out, the 3 will simply go down... the 3 links to the Y here. So yeah, let's say a 3 actually comes out. It'd be set to just a single green. Right. Now how do I make them all sync? Sync as in be on the same time. Okay. I could make it a little simpler or a little easier for myself by... Let's have this. Let's have them be slightly further apart is bad. It's gonna take up too much space. Yeah, okay. Let's not do that. Well, let's do that first and we'll see what we can do afterwards. No, it's a bit too bad. No. This produces necessary colors, but doesn't mix them properly. Could I use a nullifier? Here. I just stared a nullifier. It looks like it might be useful. If they're the same, it nullifies things. Doesn't have to throw it away, you can just nullify and pass through. Ah, okay. Okay, well, that's just a thought. I'm not actually done with the machine yet. Let's go back to this. So 3 takes longer than everything else. Everything else all takes the exact same number of cycles. I guess that's the cool thing about it, is that regardless of the number, no, it's still not going to work. It has to be slightly shorter, like this, I think. Like this. Yeah. So that when the mergers happen, like when this and this come at the same time, they will merge properly. So if it were 3, it would just be a green, yes. But if it were like a 4, the green and blue would merge to make cyan. And then, you know, at the very end, you could just make it equal to us 167. And that's how you basically produce. So this is the color that we need. This is the machine that we need to produce the color based on the number we get. Very good. This is actually fairly small. I do like it. I can make it a lot smaller if I just did this. So yeah, I do like this idea. And if it were 2, you get yellow, I believe. Yeah. Okay. Very nice. Very nice. I'm gonna keep this. And I'm probably gonna use it. It's not too big. It's, I think, about as small as I can make it without overcomplicating the wiring and everything. Could probably make it smaller, but I don't really have to. And I could just pipe the outputs through this thing over here and create the outputs. The issue now is making this the small one. We're definitely not done yet. Yeah. How? How are we even going to do this? I don't know. Alright, I think, you know what? I think that's gonna be it for this episode. I'm kind of tired out. I tired out my brain again. So I think we'll continue this next episode. I'll think about it. Yeah, until then though, hope you guys enjoyed this video. See you guys next time. Bye bye.